In today's last episode of the week 3, we will learn about the solid principles. The solid principles are a set of 5 design guidelines that promote maintainable, flexible, and easily understandable code. These principles are particularly useful in object-oriented programming, and I assume you know about the object-oriented programming as we have already learned it in the first week, third video. The solid principle S stands for Single Responsibility Principle, and its O stands for Open-Close Principle, and its L stands for Liskov Substitution, and its I stands for Interface Segregation, and lastly, the D stands for Dependency Inversion. Each one has its own statement and beauty. We will understand them one by one. But before this, let's take a look at the importance of the solid principles. In software development, the solid principles provide foundational framework for creating stable, maintainable, and efficient systems. If you don't know about them, or you know but you don't know how to apply them, or you misapply them, can result in software that is difficult to maintain, is error-prone, and requires so much resistance to change, or we can say fragile code or bad code according to Robert C. Martin. On the other hand, understanding and applying the solid principles in your code makes sure that software components are well defined, functionalities are cleanly separated, and changes can be introduced with minimal disruption. Therefore, the solid principles are more than just best practices. They represent the critical guideline for making sure the long life and adaptability of software systems. So let's get started with the very first principle, that is Single Responsibility Principle. So what does that mean? The SRP, or the Single Responsibility Principle, states that a class should have only one reason to change. In other words, a class should have only one job or responsibility. Let's understand it from Dart code. Suppose you have a restaurant class with variety of responsibilities from cooking food to handling payments. Here, the restaurant class handles cooking, payment, and cleaning. If we were to change how dishes are cooked or how payments are processed, we would have to modify the restaurant class, potentially affecting other functionalities it encompasses. For example, imagine our restaurant class handles special discounts on top of the regular payment and tax logic. We would need to adjust the handle payment method to account for the special discounts and new tax. This method can cause 4 things, but let's create an instance and see what results we are getting from this. So we got the restaurant class instance, and then we call the handle payment method from this, and then we pass the amount 100 and we set the isBirthday to true, which means that the isBirthday discount will be applied. Now if we run the code, we got the output in the console, received payment of $95 with 5 tax and 10% discount. So here in the code, what happens is we had $100, and as this was our birthday, so we got 10% discount, and there was tax, so it subtract 10 from the 100 and then add 5 to it, and then we got $95. So that is what this handle payment is doing. But as I said, this method can cause 4 things, and these are: first, the time complexity over time. As the promotions and different discounts like holiday specials, loyalty rewards are introduced, the payment logic will become more complex. And there is a risk. Suppose a new developer is not aware of the birthday discount and is only focusing on adding new Christmas discount, they could accidentally modify or remove the birthday logic, which can lead to the billing discrepancies. So in this method, over the time, if we add more promotions and different discounts, so this can become more complex over time, and the risk is that I told you, if a new developer is not aware of the birthday discount, so what things it can cause. And the third thing this handle payment method can cause is unintended consequences. Let's say another change is introduced, a loyalty card system. In attempting to integrate it, a developer might inadvertently affect the existing discount or the tax calculation because everything is muddled together. And that was also the risk. And that third point is related to the second point. In the second point, there were risks if a new developer is not aware of the birthday discount, so he could accidentally remove or modify the birthday logic as everything is muddled together. And this can also lead to unintended consequences. As I said, the developer might inadvertently affect the existing discount or a tax calculation because of everything is muddled together in a single handle payment method. And this can also lead to the maintenance issue. With each addition in this method, understanding the full impact of change becomes more difficult and potentially causing issues in unrelated features, such as if a developer is only focused on modifying the payment related logic like working with the handle payments and accidentally touches the cooked dish or clean table, it could introduce bugs in those functionalities and could bring down the whole restaurant class or whole restaurant system. If we do the same thing by following the single responsibility principle, we will do it just like this. With this division, the chef class handles all the cooking related activities, and the cashier class manages the payments, and the discount manager class manages all the discount related logic, and the tax manager handles the tax calculations, and lastly, the janitor class takes care of cleaning duties. Now each class has its own distinct responsibility. If there are changes to how dishes are cooked, only the chef class is affected. But if the payment process evolves, only the cashier class needs adjustments. And if there are new discounts or tax applied, the discount manager and the tax manager will be adjusted accordingly. Similarly, if cleaning methods change, updates will only happen in the janitor class. This separation helps in maintenance, understanding and testing each responsibility in isolation. Now, to obtain the same results from these classes as we had in the restaurant class, we would take the instance of these classes just like this. And then we would introduce calculated discount and calculated tax variables, where they're calling from the discount manager and the tax manager instances calculate discount and calculate tax. In the calculate discount, we are passing the amount and is true, meaning that apply the birthday discount. And then in the calculate tax, we pass the amount. The amount will be a double type variable with the 100.0 value initialized. Now to handle payments, we will call the handle payment method from the cashier class and pass the amount, calculated discount and the calculated tax. And then when we run this code, so we will get the same result of received payment of $95 with $5 tax and $10 discount. So that is how we achieved the same thing by following the single responsibility principle and keeping everything separated. Now each class has its own responsibility and there is no risk while modifying one and affecting the other. But that was just the example. In the real world complex application, these methods might have dozens or even hundreds of lines of code. Modifying a class that has so many responsibilities increases the likelihood of introducing bugs. By keeping each class focused on a single responsibility as we have done in here, you reduce the chance of changing in one area negatively and impacting other unrelated areas of functionality. And there are more best examples of single responsibility principle. So that's it for the single responsibility principle. And then the next principle is the solid O, meaning that open close principle. The open and close principle states that the software entities like classes, modules and functions etc. should be open for extension but closed for modification. This means when the behavior of the module needs to change, you should be able to make that change by adding new code without changing the old code that already works. Let's suppose you have a class that filters the restaurant dishes based on their type. To obtain the result from this, we will create a list of dishes and will pass the type and the dish name. Now, to filter that dish, we will first take the instance of the dish filter class, and then we will create one more variable of list of dish, and then its name is filter data. And then we call the dish filter, and then we call the by type method from the dish filter class and pass these list of dishes and also the type. Now if you want to print that filter data on that specific type, we will loop over the filter data list, and from each item we will access its name and its type and print it. So when we run that code, we will get the result something like this. On that type, we have just filtered 2 items from the dishes list that matches that specific type, but that's okay. Now imagine you also want to filter dishes by vegetarian status. you would like to modify the dish filter class something like this, which is doing the same thing, filtering, but using the isVegetarian boolean status from the dish. So by doing this, we will also add the isVegetarian to the dish and also pass it in the constructor. Now inside the list of dishes, we will get an error, which means that here we also have to specify the true or false. So we will handle them just like this. Now to filter the data by vegetarian status, we will call the byVegetarian status method from the dish filter and pass the same dishes and set this to true. Now when we run this code, we will got that vegetable filtered. We could also do the same thing by type by just commenting this and uncommenting this and pass the vegetable type in here. This will also result in same. But the reason I add this byVegetarian status in here in the dish class is I wanted you to realize what if you have some other criteria in your dish that you want to filter your dish on. So by adding these two methods, the by type and by vegetarian status in the dish filter, the problem here is that every time you want to introduce a new filter criteria, you have to modify the dish filter class. This is against the OCP or open close principles. To make this according to the open close principle, we will comment out this dish filter and will introduce two abstract classes, the specification and filter. The specification class is an abstract generic class. The purpose of this is to represent a general specification or criterion that an item of type T might satisfy. That type T means any type. And you might also be familiar with the generics as we have learned it in the first week, third video of Dart crash course. And this isSatisfied method in the specification class is the method expected to take an item of type T, which means any type, and return a boolean value true or false, indicating whether the item satisfies a particular specification or not. The idea behind this specification pattern is to separate the logic that checks if the item meets a certain criterion from the main object or system. By doing this, you can easily add new specification or criteria without modifying the existing system. And the same is this filter abstract class, to separate the filter logic and to filter the generic type items on generic type specification. Then we can do something like this. The dish type specification and vegetarian specification. Both are just a specification and implements. With this setup, if you want to introduce a new filter criterion, you just create a new class that implements the specification interface without having to modify the existing filter logic. It keeps the filtering mechanism decoupled from the specific criteria and makes our code clean and reduce the chances of bugs. This dish type specification and vegetarian specification are just the dish specifications which implement the isSatisfied method and returns true when the certain condition is matched. In case of dish type specification, when the specific type is matched, the isSatisfied will return true. And in case of vegetarian specification, when the isVegetarian was true, then the vegetarian specification will return true. And lastly, this dish filter implements the filter class with the item dish and implementing the filter method and returning dishes from the list when the specific specification for an item is matched. Then to obtain the same result, this time we will take the instances of the dish type specification and vegetarian specification. I just name it S and B. The dish type specification instantiate a class and we pass this type in here, which is when passed to the filter method will filter all the dishes on that type. And then when this B is passed to the filter class, it will filter all the dishes where the isVegetarian is true. This time the filter data variable will look something like this. From the dish filter, we call the filter method and we pass the dishes and pass the B, which means that it will return all the dishes where isVegetarian is true. Now, if we run this code, this will result in the same vegetable type dish. And then also, if we pass the S in here, so this time this is going to result in the spicy dishes. And also, if we pass the vegetable in here, so the same thing will happen. But this vegetarian status was just to show you if there is a new criteria added, so what will happen in that case. So now you might ask, in that dish filter method that we just comment out. When we add this by vegetarian status, filter method was not the modification of the existing code, meaning that we are not modifying that existing by type method, but we are adding just a new by vegetarian method. That was not the modification. Then why we create such abstract generic classes and we did these kind of implementations? So there are few reasons you need to understand if you have this kind of confusions in your mind. The first one is with this dish filter class. Even though you are not changing the existing method behavior, but adding new methods to the class still represents a structural modification. You are altering the class structure every time you introduce a new filter method. And this also causes the maintenance issue. Each time a new filter criterion is added, you have to revisit the dish filter class and introduce another method. It leads to a bloated class with so much methods, each for different criterion. Over time, it leads to a very complex class with so much methods, each for a different criterion. So over time, this method could become more harder to maintain. And this method was also violating the single responsibility principle, because this dish filter class would end up having too many reasons to change, and so violating the single responsibility principle. Adding each new filter criterion would be another reason for this class to be changed. Remember though, by open-close principle, when we say closed for modification, it doesn't just mean not altering the existing line of code, but also indicates that the behavior of a module should not require constant changes like addition whenever there is a new requirement needs to be added in a class. To make this open-close principle more clear, let's take one more example. For example, you have this discount calculator class, and it is calculating the discount based on the specific type. There is nothing wrong with this discount calculator class and this method. Let's create the instance and implement it. So we got the instance of the discount calculator. Then we create an amount variable with the 100.0 value initialized. And then we print from the discount calculator instance, call the calculate discount method and pass the type of the discount and also the amount. So let's run this code and we got this result. On the birthday, we have 10% discount, and on Christmas, we have 20% discount. And there is nothing wrong with this method. But one thing that you need to keep in mind is that whenever there is new type of discount, you would have to modify the calculate discount method, and you are breaking the open-close principle here. This approach can cause problems. That is because there are constant changes required, and thus we are modifying the discount calculator. And this code is also not flexible at all. We are hard-coding the discounts and making our system rigid and hard to maintain. With following open and close principles, we create a discount abstract class with calculate method, and this class is implemented by the birthday discount and Christmas discount with their own discount calculation on the amount. And the discount calculator is simply applying the discount on the amount. With this approach, let's say if we want to add new discount type like the Easter discount, so we can simply create the Christmas discount and implement it with the discount abstract class, and the existing code is remain untouched. So let's go and achieve the same result as we had this rigid and hard to maintain discount calculator. So here we will comment this out, these two print statements, and here we will do to obtain the same result from this. In the main method, we will do something like this. We have the birthday discount, and then we are instantiating or creating the instance of the birthday discount, and also we are instantiating the discount calculator. And in the discounted amount, we apply the discount of that birthday discount on that specific amount, and then there we go, we print it. And same for the Christmas discount, we call the apply discount method from the discount calculator and then pass the Christmas discount, so that Christmas discount will be applied on that amount. And then simply we are printing that discounted amount in here. Now, if we run this code, this will result in SAM. And you might think we have specified the discount abstract class in here, and then we are initializing the value to this birthday discount variable, the birthday discount instance. This is because of the polymorphism. The polymorphism allows us to treat different objects of different classes as instances of same common interface or superclass. We are declaring the type of the variable as a discount, and we are initializing it with the instance of the birthday discount. And by doing this, we means that any method we call from this birthday discount will be the implementation of this birthday discount class here. So if we declare it like this and we call the calculate method in here, so any discount instance like the birthday discount or the Christmas discount is passed in here will use its own implementation that is declared inside the specific class. Like we declare the birthday discount with the type of discount class and its implementation is birthday discount. So now when we pass this birthday discount inside this apply discount class, so from this birthday discount class here, it calls this calculate method, and this calculate the discount on that amount, and here we have printed it like that. So that was two examples of open and close principles. So the third principle of Solid is Liskov substitution principle. Liskov substitution principle states that an object of a superclass should be able to be replaced with objects of subclasses without affecting the correctness of the program. In simple terms, if you have a class B that is the subclass of A, then you should be able to use an instance of B whenever you use an instance of A without causing unexpected behaviors or errors. It means that anywhere in your code where you expect an object of class A, you should be able to provide an object of B, which is the subclass of A, without any issues. So let's take an example. Suppose we have a rectangle class with the properties of width and height, and also the methods of setWidth, setHeight, and also to calculate the area. In this example, the square is the subclass of the rectangle class, but when you modify its width, its height also gets modified to ensure it remains the square. This can lead to unexpected behavior and inconsistency in our code. When modifying one side of the square, it modifies both width and height. And if you expect it to behave exactly like rectangle, so it doesn't. To better align this with Liskov substitution principle, a potential approach is to design these shapes differently, or perhaps do not inherit the square from the rectangle. For example, in this refactored version of the code, both rectangle and square implement the shape interface. Each retains its own method and properties without any unexpected overrides. By doing this, both the rectangle and square follow the Liskov substitution principle, and any function expecting the shape can handle either shape without surprises or any unexpected behaviors. Consider the following utility function. This function can be called with any object that implements the shape interface. In the main function, here both classes have different internal details, but both adhere to the square shape contract of calculating the area. So an instance of square or rectangle can substitute for an instance of shape without issues and following the Liskov substitution principle. So in more simple words, a Liskov substitution principle from Solid is a rule for making sure that a child or subclass behaves in a way that any code which is expecting the parent or superclass won't get expected surprises or any unexpected results. For example, imagine you expect a duck, but getting something that looks like a duck but can't quack. The Liskov substitution principle says that if you label something as a duck, it should quack like one. The Liskov substitution principle is designed by contract principle. For example, think of a contract as an agreement between two parties. In coding, when you write a function or method, you are making an agreement that if someone gives you certain input like duck, you will do certain things, expect it to quack. So the Liskov substitution principle says that if a new kind of duck is created or a subclass of a duck, anyone using it should still be able to expect it to quack. This means that any code that's been written to handle the original duck class should also be able to handle this new kind of duck without any problems. So that was the Liskov substitution principle. Now we are going to learn the solid fourth principle that comes from the letter I, which stands for interface segregation. So what does that mean? Interface segregation. The interface segregation principle states that no client should be forced to depend on interfaces that does not use. In other words, instead of having a large encompassing interface, it's often beneficial to break it down into smaller and more specific interfaces so that the clients only need to know about the methods that are of interest to them. This ensures that implementing classes are not burdened by the need to implement methods that they do not require. For example, imagine you have an interface, all-in-one printer, that has the method of print document, scan document, and also fax document. But what if a particular printer model does not support scanning or faxing? Implementing this interface would force that model to implement unnecessary methods. A better approach with following interface segregation principle, we will create 3 separate interfaces or abstract classes in our Dart programming language. Now, if a printer model supports only printing, it can just implement the printer interface. If another model supports both printing and scanning, it can implement both printer and scanner interfaces. By segregating these interfaces, we avoid unnecessary bloat in our implementations and provide a clearer and more flexible structure. Now, relating back to our shape example, which we were discussing in the Liskov substitution principle. Instead of a broad superclass like the rectangle, which could encompass many methods, we defined an interface shape, which only keeps an area function. Now imagine if shape interface or our abstract class had multiple methods such as area, perimeter, diagonal, and number of edges. Now, if a class like square or circle implements or extends that shape interface, it would be forced to provide an implementation for all of these methods, even if some of them are not meaningful or relevant to circle or the square. For instance, while area and perimeters are directly relevant to the square class, but the methods like diagonal could also be, but something like number of edges might not be relevant for circle. Including this method in a general shape interface would then force a circle to also implement this number of edges method. And this method does not require in here. And this could be a clearer violation to interface segregation principle. The point of interface segregation principle is to prevent such scenarios where you are burdened with the methods you don't need. Instead of one do-it-all method, just like this one, you might have separate, more focused interfaces like the area calculatable, perimeter calculatable, and diagonal calculatable, etc. as we have here for the printer, scanner, and the fax machine. And a real-life example of interface segregation principle would be if we have an interface character and in our model we have a warrior, an archer, and a magician. And in our character interface, we create the methods or the behaviors of the warrior, archer, and a magician. So the classes like warrior, archer, and a magician have a specific character, and a warrior cannot do magic, and a magician cannot be an archer or a warrior. So in that case, if we keep the character interface with the methods of these 3 character behaviors, this can lead to unnecessary implements in each class and clearly violating interface segregation principle. So to better align with the interface segregation principle, we can create different interfaces such as warrior character, archer character, and magician character, as we have done in here. For the printer, scanner, and fax machine, again I'm saying that. So that is what the interface segregation principle is. The Solid principle overall are very useful and they make our code more scalable, maintainable, and testable. Sometimes in our code, we all apply some of these principles and also misapply them, and we aren't even aware of it. So in order to understand and want to being aware of every method and a class or a specific task we can say in your application, in your software, you must know about these golden principles which will really help your code to be more improved and being flexible and maintainable and lastly testable. So the last principle of Solid, which comes from the last D, which stands for Dependency Inversion Principle, states that high-level modules should not depend on low-level modules, and low-level modules should not depend on high-level modules. Both should depend on abstractions. And the abstraction should not depend on details, but the details should depend on abstractions. I know at first it might be a little bit abstract, but let's break down that statements that I just said. First, high-level modules should not depend on low-level modules. Let's look at an example where high-level module depends on low-level module. In this example, the restaurant is high-level module or class, depends on banked payment gateway class. This means that the restaurant class is tightly coupled to the bank payment gateway class. If we want to change the payment gateway, we would need to make changes to the restaurant class. And this is not a good design because it makes code less flexible and maintainable. If the software expands with the time and we need to add new features, we may not be able to do so without making changes to our restaurant high-level class. So that is what happens when the high-level module or class depends on low-level module or class. Now let's see what it means when we say low-level modules should not depend on high-level modules. So in this example, the low-level module depends upon high-level module, which is quite opposite to the first example. In this example, the bank payment gateway class depends on the restaurant class, which is our high-level class. This is also not a good design because it makes the code less flexible and maintainable as we had in the first example where the high-level module were depending upon the low-level module. Now in here, same as we had in the first example. If you want to change the restaurant class, we would need to make changes to the bank payment gateway class. So again, this is also not a good design. Now, as you understood and seen how low-level modules depends on high-level modules and how high-level modules depends upon low-level modules and what problems they can cause. Now, let's understand these two statements together. First, high-level modules should not depend on low-level modules, and also the low-level modules should not depend on high-level modules, but instead both should depend upon the abstractions. So in this example, the restaurant class no longer depends on the specific implementation of the payment gateway interface. Instead, it depends upon the interface itself. This makes the code more flexible and maintainable. If you want to change the payment gateway, we can simply change the implementation of payment gateway interface in the restaurant class, and we do not need to make any changes to the restaurant class itself. So this example better align with the dependency inversion principle. Our high-level class restaurant is not depending upon the concrete implementations, but it instead depends upon the payment gateway, which is an abstract class, or in other programming languages we can say an interface, which does not have the concrete implementations. And this payment gateway method is implemented by the different payment gateways, like bank payment gateway implements the payment gateway and finally overriding the handle payment, and the same for the credit card payment gateway, and again it is implementing the payment gateway and is overriding the handle payment, which is the polymorphism in object-oriented programming. So now let's understand this. Abstracts should not depend on details. Abstractions should not depend on details, but instead details should depend on abstractions. So in the context of object-oriented programming, details are the concrete implementations of the abstractions. For example, the bank payment gateway class is the detail of the payment gateway interface or abstract class. And these abstractions are the general concepts that are implemented by their details, as this abstract class or an interface is implemented by the bank payment gateway or the credit card payment gateway. The dependency inversion principle states that abstraction should not depend on details, instead details should depend on abstractions. This means that the return class should not depend upon the specific implementation of the payment gateway interface, but instead it should depend on the payment gateway interface itself. This makes the code more flexible and maintainable. So that was our dependency inversion principle, and you will get to know more about this when we go for real app development with clean architecture. So we learned all of the solid principles. Now let's summarize each principle. The first principle of solid was single responsibility principle, which advises focusing each class must only have one reason to change. In other words, every class should have only one single responsibility. This ensures readability and maintainability in our code. And the second principle was open and close principle. The open and close principle tells us that the classes should be open for extension and must be closed for modification. This promotes scalability in our code. And the third principle is Liskov substitution principle. The Liskov substitution principle, or LSP, tells us that the subclasses must be used interchangeably with their superclasses. This principle enhancing code usability and maintainability. And last but not least, interface segregation principle. The fourth principle of solid tells us that the client should not be forced to depend on the interface it does not use. This advocates for specific client-focused interfaces and consequently reducing unnecessary dependencies. And lastly, the dependency inversion principle that we just understood underscores decoupling high-level modules from low-level details through abstraction and results in enhancing flexibility and future-proofing code. So that were 5 golden design principles that every software developer should know about if one wants to write maintainable, flexible, and easily testable code. So that's it. See you in the week 4.